All right, to wrap up the electricity unit, our last topic to cover is about producing electricity. How do we produce the current that we need to run our circuits and all that kind of stuff? We've been looking at two sources really. The first one have been really about batteries. So what goes on inside of a battery that produces electricity. The other one was our household outlets. And for us now to understand, well, how do we produce the electricity that comes out of those outlets? But first, the battery. Well, when it comes to the battery, what really happens inside of these things is about chemistry. And we've looked at chemistry and the connection to energy before. We've looked at stuff like reactions that would cause light or heat to be produced. We looked at glucose. That's another way of storing energy for us in terms of biological organisms and the breakdown of glucose for energy. Well, the same thing can be said for certain chemical reactions that produce the movement of electrons, and that is what we see happening inside of a battery. Batteries make use of basically two substances, and again, depending on the type of battery that you're looking at, whether it's a zinc carbon or lithium ion, they'll use different materials, but essentially the theory is the same. There is a chemical reaction happening inside of these things that result in the buildup of electrons around one of the substances. And this substance will then be considered to be the anode, or what we call the negative terminal. It is the terminal that has sort of the buildup of electrons. That creates this electric potential, and these electrons want to get to the other substance, the cathode or the positive terminal. So all that requires is for us to basically connect the two terminals together, and we have, if it's a complete circuit, the movement of current. This is a battery, and that's what's happening inside of it. It's a chemical reaction, and it produces this electric potential where we see the buildup of electrons on one terminal, and those electrons want to get to the other terminal. Now, similar to any chemical reaction, eventually, if you don't have enough reactants, you're going to run out, and then the reaction stops. The same thing can happen with batteries, and when that happens, basically the battery is officially dead. However, rechargeable batteries make use of electricity, basically when you plug it into a wall to recharge it, that reverses the chemical reaction, and it's almost like you move the electrons back to where they started from, and then you unplug it, and the battery's charged again, and you're ready to go. Batteries produce direct current. Electrons move in only one direction. I've been taking clips off of TED Ed videos on batteries. They have a great video on how batteries work, so if you get a chance, you might want to check it out, but that's where I'm getting these clips from. They're great. Now, when it comes to the electricity that comes out of our outlets, that electricity is produced in a different way, and I'm going to need to use a simulator to show you just the basics around this. Let's take a look at this experiment here. That's a recreation of Faraday's work. Faraday was a huge player in our current understanding of electricity, and in particular, the use of electricity in circuits. Now, his experiment was this. We have here a coil of wire, and this coil of wire is connected up to a voltmeter, and you can see there, and you'll see this the needle sort of indicate this voltage. If there's any electric potential happening here, you'll see this needle move. This light bulb here is for added effect, and basically, if it lights up, you know that not only are we getting voltage, we're also getting current, and we know that those go hand in hand together. This is a magnet over here, and you'll notice that when we pass the magnet through, or even a little bit around it, can I even move it around it? Will it do it? Yeah, it does, but it sort of skips. But if we move the magnet through or around this wire, you'll notice that we end up getting this voltage being produced that sort of slides back and forth. This is that electric potential that we looked at, and that causes that movement of electrons in this wire, and then that is also shown here by the light bulb lighting up. This is an important concept. Basically, it's this magnetic field. I'm going to show you this magnetic field around the magnet here, and there they are. How it works is this. When a magnetic field cuts through a conductor like wire, it causes the electrons in that conductor to move. Basically, you end up with current electricity because, again, it's that movement of electrons, and we're seeing that there with the voltage. You can see the needle moving back and forth, and the light bulb lighting up. All right, and it doesn't really matter. I can flip this magnet around and go the south end first. What we're actually seeing, though, is the same thing, and as long as that magnetic field cuts through or passes through this conductor here, the electrons in that conductor will move. And that's essentially how a generator works. So from that quick demo, we know this. If we have a coil of wire and we have a magnet, move either the coil of wire or the magnet past each other, and it will cause the movement of electrons in that coil of wire. It doesn't matter if it's the wire moving or the magnet moving. You just got to have one of those two things moving, so that way you have that magnetic field moving through that coil of wire and you end up having electrons moving. So let's scale it up. Now we start talking about, well, let's not produce just a little bit of electricity here. Let's produce enough electricity to power a city. And generators basically are made up of these large coils of wire and really strong magnets, and you'll either move the coil of wire or the magnet past each other and you start generating electricity. You'll notice that when we did the simulator, that as I moved the magnet through the coil, that the needle would deflect one way and then back the other way, then this way, then that way. It was flip-flopping back and forth. Either way, you're having the movement of electrons, and that is current electricity. But that also explains the reason why the current that we get out of our outlets is what we call alternating current, which means that it's current that moves back and forth, back and forth. It is a byproduct of how generators work. Basically, this magnetic field cutting across and back, you end up having this movement of electrons in one direction, then flip-flopping and going the other direction. Same thing with the voltage. It goes from positive to negative, positive to negative. And that is the reason why the current moves back and forth, back and forth. So the generation of electricity using generators produces alternating current. And now you see why. All right, so I have a large magnet and I have a large coil of wire, and I have to move one or the other to create this current electricity. How do I move these things? If these are relatively large, do I just have a whole bunch of people moving a magnet or spinning a coil? No, obviously we're going to try to make use of other things that can do that for us. And this is how we have different types of generators. How can we take either a magnet or a coil of wire and make it move? Well, if we were to take either the magnet or the coil of wire and attach it to something like a water wheel, we could have water moving past that and cause that water wheel to move, and along with it, the coil of wire. And now we're producing electricity. Maybe we attach it almost like a fan blade type of thing to it and let the wind spin it. We could also do something similar to that water wheel, and instead of just moving water, what if we heat up water to the point where it's boiling and use the steam to turn that, what we call turbine, and then in turn, turn either the wire or the magnet. Either way, we're using things out there to help spin and move this magnetic field or the wire through the magnetic field to start producing electricity. And that's the reason why we start hearing stuff like hydroelectricity. That's using moving water to help turn either the coil of wire or the magnet inside of a generator. We have wind energy. Like we just said, it's using the wind to move either the wire or the magnet. We also have stuff like nuclear energy or coal burning plants. Basically, they use that energy to heat up water, get the steam, causing the turbine to move or spin, and then in turn, the magnet or the coil of wire to spin. So ultimately, these are just different ways of moving either the coil of wire or the magnet so that we can start producing electricity. So which way is the best? Which way is the best way to actually cause that coil or that magnet to move or spin? Well, each have their sort of positive points and their negative points to it. Let's start off with coal. We could burn coal and heat up water and cause that turbine or that coil or magnet to spin. The thing is that we release a lot of carbon dioxide. And in fact, there's been a movement to sort of reduce the amount of coal that we're burning to produce electricity. Okay, what about nuclear power plants? Well, they're great, and relatively speaking, they don't release any sort of carbon emissions, but we're left afterwards with this waste that we now have to dispose of. And this is stuff that you just don't want getting out into the environment. So the nuclear waste that's generated from a nuclear power plant often has to be like buried deep within a mountain so that it doesn't leak out and contaminate the environment. All right, well, what about hydroelectricity, using water? That's great. I mean, it's clean and you're always gonna have running water, and that's true. The only downside to that is not everyone has access to running water. Now, we all don't live near large raging rivers that could then be used to spin either a coil of wire or a magnet. Same thing with wind. We all know that some days are better than others, and when it's not windy, you might have a problem there as well. So even though we don't have the perfect way to generate electricity, there is this movement and this important need for us to move towards renewable energy sources. So what does that mean? Well, renewable energy sources are energy sources that we can use and harness to create electricity. And those sources of energy that we use replenish themselves at a much faster rate than we use them up. For example, in and around Niagara Falls, we have 2 hydroelectric dams that produce electricity from moving water. In other words, the moving water spins the magnet inside of a coil of wire, and that generates our electricity. Now, that moving water is always there. It renews itself really quickly. So in that case, we would call that a renewable energy source. It's there. We don't have to wait long to get more moving water. We can then use that moving water to then create more electricity. Coal, on the other hand, is different. We could use coal, burn that, and then use that to heat up water and use the steam then to turn that magnet or that coil of wire and produce electricity. But the thing is it takes millions of years to produce that coal. So once that coal is burned up, we have to go and get more. But the thing is eventually we're going to run out because we're going to use up the coal faster than the coal can be reproduced. We have left out one important source of energy that doesn't really fall under generators and it doesn't fall under batteries, and it's solar panels. This makes use of a material inside of the panel, such as silicon, that when it's exposed to light, photons of light, it excites the material in here and causes the movement of electrons. And there is your electric power. This is another example of a renewable energy source because it's coming from the sun. It is a constant sort of energy source for us, providing that we don't have clouds in the way. But this is another technology that is getting better and better all the time and provides us another source of electrical power besides batteries and besides trying to harness power from something like a generator. So that is basically the lesson and us thinking about how we get our electricity. But it is something that you will take up again later on in your science courses because it is such an important thing that we need to consider moving forward. For us as a society, globally, electricity is something that allows us to do work. But with it comes this need for us to come up with ways that allow us to generate electricity in large amounts, but in a way that's responsible and it's not going to destroy the environment. All right, that is the electricity unit. What I'm going to send out to you guys today is that circuit assignment. So this is something that we've been building up to, and today I'm going to send it out to you. And it's not going to be due this week. I'm going to let it sort of have you hand it in next week because, again, I know you got a lot of stuff on your plates. We've got the quiz coming up this Friday. Don't forget, review is going to be happening on Wednesday. And I want to make sure that I give you enough time to play around with it. The assignment itself is not too tough. It just really pulls on the stuff that you've learned before from our electricity unit. It's just going to get you to try to build a circuit, and I'm going to leave it really wide open for you so that way you can build a circuit that you feel comfortable with and hopefully have a circuit that works, because that's important. But what you're going to do is answer the questions, submit in your circuit, and that's basically your assignment. So I'll be posting up a separate video explaining all of that, but I just want to give you the heads up now that we are officially done the unit on electricity. Well done, everybody. Well done.